Hello everybody and welcome back. Missed you all, and let's get started on the second half of chapter 9. Now those of you following along at home did notice that we skipped sections what was it 9.2 and 9.3. Those involved ellipses and hyperbolae. If you want to learn about them, they're pretty cool, but we're not going to focus on those this year. If we were in class, we would have. Now on to section 9.5, parametric equations. When you learned to graph, how did you graph the equation below? So some things that you might be saying is, the old lazy person's way of doing it. You might have grabbed your calculator and graphed it. Really what I'm going after here, some of you might be saying, we know how a parabola works because this is quadratic. What I'm really looking for here is that you guys use the XY chart in order to graph stuff when you first learn how to do it. And the reason why I bring that up is because it's going to help us out when you learn this new thingy called parametric equations. So in the olden days, we had an independent variable and one dependent variable. By olden days, I don't mean, like the medieval times. I mean when we were in Algebra 1, when we were in Algebra 2, when we were in geometry, that type of stuff. Those equations that you graphed in those other courses and this course up until now were called rectangular equations. When you have y equals f of x, it's called rectangular. Now bear with me for a second when I tell you we can graph using an independent variable and two dependent variables. The new variable that we introduced, it's going to be called a parameter. So there's a vocab word for you. It tells us how long it takes to get to a particular point, and that is why we use the variable t for time. Parametric equations take on the form x is equal to f of t and y is equal to g of t. Now I know this is going to be a little bit outside of the realm of comfort for some of you, but this thingy right here, it is a toy. Well, no, it's a teaching tool. That's what we'll call it. It is called an Etch-a-Sketch. And I hope every single one of you has seen an Etch-a-Sketch before. If you have never seen an Etch-a-Sketch before, what it does is, you probably can't read it, but right here, this says horizontal dial, and this right here says vertical dial. And when I twist the horizontal dial, it makes the sketchy thingy go left and right. When I twist the vertical dial, it makes it go up and down. Notice that when I make the scratchy thing go left and right, this knob over here does not affect this knob over here. Same thing on this one. The only thing that affects the location of the sketchy point is the amount of time that has passed since the beginning of my experiment. Now if I want to start my experiment all over again, I'm just going to take this off screen for a second. I don't know if you can hear that, but that's called a shaky doodah. It shakes away everything. Now what happens here is when the vertical dial and the horizontal dial move in conjunction with each other, you can get a diagonal line. You can try to get somewhat of a circle. I don't know, I'm not too upset about that circle. That's actually pretty darn good. There are some things, if you want to Google it, just Google Etch-a-Sketch drawings. There's a lot of stuff. People have made like the Mona Lisa on this thing. But basically, an Etch-a-Sketch is a parametric grapher. So just definition of a plane curve, if f and g are continuous functions on an interval L, the set of ordered pairs f of t, comma g of t is called a plane curve C. And the equations given by x equals f of t and y equals g of t are called parametric equations for C, and t is the parameter. Bunch of vocab words in there. Plane curve, parametric equations, parameter. All of those are important to know. They look a little bit intimidating right now, but trust me, they're not that intimidating. Now, things to point out here. We have it says continuous functions, so that means all of the numbers, not just integers. So we have to have all the numbers in between there. So I'm just going to skip right to this. This is we are graphing a set of parametric equations by hand. And the way that we do that, we essentially make an XY chart. But X and Y are both dependent variables. There's a third independent variable that we need to add to this XY chart. So now what we actually have is a TXY chart. Now, if you remember back to when you learned how to use an XY chart, in order to graph using X and Y, you really just had to make up whatever X values you wanted in this situation, and it didn't matter what they ended up being. Anything is fine, right? So I'm just gonna choose some numbers. Let's say I choose. Let's start with some negatives, and we'll go up to positives as well. Sorry about all that noise. I've realized I'm going to need a straight edge here in a minute, and I'm realizing I don't have a straight edge, so we're going to improvise. There we go, with my faculty ID. So I'm just going to make up some t's. So let's start at -2. I might go up until I can recognize what the curve is going to look like. Hopefully at some point I can see what the curve is going to look like, right? All right. So -2. In order to find out where this particle is in the x direction and the y direction at -2, all I have to do is plug -2 into the x equation. So -2 squared. Just to show you, this is the scratch work that's going on in my head. -2 squared minus 4. Can you guys see that up there? -2 squared is 4 minus 4 gives me 0. And then over here I have to do -2 divided by 2. So x is equal to -2 squared minus 4, and y is equal to -2 divided by 2. -1. All right? So I know that at t equals -2, the particle is at the location of 0, -1. The trick here is you don't know exactly when you have enough graphed unless you are graphing it while you're doing this. So let's see here. I'm realizing that my straight edge is not long enough, so we're going to use this box right here. I'm just going to throw on some axes right here. Let's see right here. That look like good enough axis to you guys? I hope so. Is that dark enough for you guys to see? Maybe I'll go back and trace over it to make it a little bit darker. Alright. I hope you guys can see that axis. Now, I know where this is going, and I know that I'm not really going to go really big or really high, so I'm going to make every other tick mark worth 1. So 2 tick marks to 1 unit. And you can just experiment to figure out what the good spacing is on this. Might help to put some more points on here, but we'll get there. -2, -3, -4. Hopefully I don't go any further than that. I don't know if I will. 1, 2, 3, 4. Generally, I'm kind of lazy about labeling my graphs. The least amount that I can do, I'm going to do that. Let's go up to 5 over here. Alright, cool. So I got some stuff labeled. So the first point that I'm at is 0, -1. So 0, -1. Alright, let's use some color coding here. What do you guys think about pink? Put the dot right there at 0, -1. To find our next point, let's just go to integers. Now, I am going to point out that the numbers between -2 and 1, I can plug those both in here, but I don't want to plug in -1/2 in here because that's just hard to calculate. Doing -1 squared, that's just 1 minus 3 gives me -3. Over here I got -1 divided by 2. Well, -1 divided by 2, I don't know what it is, but hey, doesn't it look like -1/2? So I've got -3, -1/2, right about Chihira, right? Now again, all of those points in between are valid, so I know that it's just going to roughly be some sort of curve in between those two. I don't really know what this is looking like, so I'm just going to put some more points. 0 is another easy point to put down. 0 squared minus 4 gives me -4. 0 divided by 2, well, 0 divided by anything is 0. So, -4, 0, right here. And you can kind of see it's forming some sort of curve. I really don't know where this is going yet, so I'm just going to keep throwing down more points until I can see what the curve is. Let's see, 1 squared minus 4. Feels like I've done this before because it's positive 1 minus 4, -3. 1 divided by 2, I've done this before, but I did the negative there. So -3, 1/2 is another point. Oh, gee, look at this. This fails vertical line test. That's not a function. Well, okay, so it's not a function in the traditional sense. It's a parametric function, though. Let's see. Let's make some more points. 2 squared minus 4, 0. 2 divided by 2, positive 1. Let's just throw one more down for good measure. 3 squared, 9, minus 4, 5. 3 divided by 2, 3 halves. Alright, so let's graph those. What did I miss? 0, 1. 5, 3 halves. Ooh, way out here. Okay. I'm just going to try to sketch something in here that looks somewhat curvy. I know I want it to be nice and smooth. I don't want to put any corners on here. Now that you guys know what a corner is, that comes up in calculus next year. Okay, I'm not the best at sketching the smooth curves. You just want to get them kind of smooth there. Now the downfall to this is we only have 2 dimensions that are shown here. We've got lefty-righty and uppy-downy. Again, lefty-righty known as the horizontal component. When I'm on my Etch-a-Sketch, that's the left knob. When I'm here, that's the x-coordinate. This determines the horizontal movement. The y-coordinate is my right knob, my vertical knob here. The one thing that I'm missing here is showing how t acts on this. In order to show t on this, I just need to show what direction this particle moves. And if I look at this, starting at -2, I'm at 0, -1, so I'm here. And then I'm going to move to -1 at -3, -1/2. And I'm going to go up here, and up here, and up here. So bear with me here. I'm going to try to show you the motion. This particle, if you imagine the tip of my pen is the particle, it's going to go around this curve like here. So we just show the direction using arrows. Throw enough arrows so that anybody reading it can actually see the particle that you're representing here moves in this direction, right? Just to show you what's on the next page, it is the exact same graph. I even used the same domain here. The kind of crappy thing about this is you're not officially told what the domain is for the for t. I guess you can kind of figure it out with some of these using the traditional ways of figuring out domains and ranges and all that stuff. So try this guy out. Pause the video so you can. I'm just busying myself grabbing some graph paper because apparently I didn't come prepared today. Alright, cool. I got my graph paper. I thought I actually had a piece of graph paper on this page, but apparently I don't. I think it's on the next page. Yes, it is. So I just want to point out some stuff. You should resume now if you're completely lost. We want to make a T, X, Y chart. I got plenty of space, so I'm just going to spread that out as much as I can because that's the only work I need here. I will point out that since I've got square root of t, I hope you guys can remember way back when we talked about square roots, you're not allowed to plug a negative into a square root. So the domain of this is just going to be positive, well, not positive, whole numbers because we do still have 0 in there. So you can start at 0 and you can go up until you see a pattern on this. So I'm like, let's go 0, 1, 2, 3, 4. Does that sound good to you guys? 4 is good enough for me. I'm just thinking, because I'm doing square roots. I got 3 perfect squares on here. I could go up to 9 if I want to, but that's going to be a lot of points. So looking here, 0, x is the square root of 0. So that's 0. Y is 2 minus 0, 2. Should I do the rest of these and then plot them, or should I graph them as I'm going? Alright, cool. You guys are right. Let's just do this really difficult math here. Square root of 1. 1. 2 minus 1. 1. Alright, cool. Still difficult. 2. So square root of 2. Oh, shoot. Square root of 2. Okay. Idiot machine. Can you guys see that? square root of 2. 1.414. Oh, okay. 2 minus 2. 0. Square root of 3. Please, Mr. Idiot Machine, tell me 1.732. 2 minus 3, negative 1. Square root of 4. Okay, cool. Integer, 2. 2 minus 4, negative 2. Alright, cool. Now I've got some graph paper, and ignore this, I used it for the parabolae from the last lesson. Well, maybe that's why I should have made it more compact so we could actually see the graph when we get here. Oops. Viewing screen of my phone fell over, so let's put it somewhere where it won't fall over. Okay, so let's see. Starting at 0, 2. Whew. You know what? I've got some decimal values here, and I see that I'm going between 2 and negative 2, 0 and 2. I really don't need this to be that big of a graph, so let's make 4 tick marks into 1. That means 8 tick marks is into 2. That's as high as I need to go on the y. 1, 2, 3, 4. 1, 1, 2, 3, 4. 2. I think that's as high as I need to go on the x. And for the y going down, I'm going to have to go down to 1, 2, 3, 4. Negative 2. Alright, cool. Did I space? That looks just kind of weird. No, it's all spaced out right. Okay, cool. So 0, 2, 0, 2. Ooh, color coding. Gotta remember the pink. 0, 2, 1, 1, 1.414. Okay, so a little bit before 1.5, and 0. 3 would be at 1.73, so a little bit before 3/4, and negative 1. So right Chihira, and negative 2, negative 2. I don't know, that looks like pretty darn easy to draw the curve in here. Ah, cool. And I will point out that this is going to extend further down because I can make my my t-values bigger, but it is not going to extend further to the left or up because I cannot make my t-values smaller. And then just tracing this, starting at 0, 2, 1, 1, root 2, 0. Okay, so it looks like I'm going this direction. All right. So graphing these should not be difficult. It is somewhat tedious, but it should not be difficult considering you're just doing like Algebra 1 type work. Just to verify, there's where the graph, or what the graph should look like, not where the graph should look like. That's just a weird way of saying things. Hey, 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 we all have a fancy machine that takes away tedium from a situation and makes it a little bit easier. And what I'm trying to say here is you can use your graphing calculator for this. In order to change your graphing calculator into parametric mode, you go into the mode menu. So for those of you who don't know where the mode is, I'm going to try to make it easy for you guys to see my calculator. Mode is right here. You go into mode, and some of you do not have these this color screen. If you have one of the Casios, I'm sorry, I don't know how to do this, but from what I remember from previous years, it's not that difficult. If you don't have a TI-84 or a TI-83, a Texas Instruments, whatever, I would recommend Googling Wabbit Emu, and you can get in touch with me. I can get you the operating system to get Wabbit Emu working. You can get it on Android, you can get it on Windows. I think you can get it on Mac OS. I know it does not work for iOS, so that kind of stinks. But whatever. Whenever you get your calculator working, go down to the row that starts with function. If you got one of the grayscale screens, I think it just says FN. Go over to parametric, or it says par or para. One of those. Hit enter, and nothing happens. In order to see stuff that happens, you actually have to go into the menus up here. So just to be clear, that's the next slide, is to go through these menus, and I would actually increase the size for you guys to see it. Now, to see what happens with all of this, I just want everybody to go to the zoom menu. You will see nothing happens. The zoom menu is exactly the same. Go to zoom standard just so that we can get everything looking exactly the same on all of our calculators. You can see that the graphing window that it pulls up looks exactly the same. The trace looks exactly the same because we don't have anything graphed yet. Where we see some difference is if we go to the y equals menu. And in the y equals menu, you will see you've got an x1, y1, x2, y2, and you can actually see my x3 and y3 on down have been populated. That's for stuff later on. I didn't want to spend my time in front of you graphing it. So you can start like putting in functions. So like if I wanted to put in the last function that we had there, I could put in square root of, and to get t, I can either hit alpha t, or the really cool thing is this button that you've always referred to as the X button, it's not the X button. See how it says xt theta n? It's now the t button. It's actually just the independent variable button. You can hit it and you get t. And again, I'm just graphing the last one that we had. So I've got, notice how the equal signs don't become black here? That's because in order to graph a parametric function, you have to have both equations there. If you do not graph the parametric function. So here I got to do 2 minus t, and now see how it's blacked in automatically. Just like in the function mode, I can go over here and hit enter on either one of these equal signs and turn off the graph, and that's what I've done down here so we don't have to see those graphs that come up later. Now before we hit graph, to see what this graph looks like, we're going to go over to the window because that's important as well. The window is it causes some difficulties for people when they're trying to, like when you're doing homework tonight or today or whenever you do it. A lot of times the Tmin and the Tmax screw people up because we get to determine what domain we're graphing over. Just like in those last problems where we decided where we started t and where we ended t. The calculator makes that decision. When you're in function mode, it's easy because your xmin and your xmax are just the leftmost point and the rightmost point of the window. Here you actually have to declare it. So you'll see it actually goes from 0 to 2 pi. I would normally ask you guys why you think it goes like that, but I'll just tell you. The reason is because sometimes you use trig functions and it wants to go through one period of the trig function to get the full graph, because sometimes graphs like loop back on themselves. This t step, really don't mess around with that. What that does is it's just like the x step or the x res on your, not x res, the x step on your function mode. It determines how much they move for each t value that they calculate. So like it's going to start at 0, and then the next point that it's going to graph is 0.13 for t, and then 0.26, etc., etc., etc. The bigger you make this, the worse your graph. The smaller you make it, the longer it takes to graph. And then you can see the traditional xmin, xmax, xscale, ymin, ymax, blah, 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 blah. Zoom, we already went through that. Nothing has changed there. I will take you to the calc menu, so I'm hitting second trace. Notice the calculate menu has much fewer things in there. It has the useless value button. It has dy dx, you don't know what that is. It has dy dt, you don't know what that is, and dx dt. So the only thing that you know what it is value, and it's useless because all we have to do is hit trace. It graphs exactly what we graphed last time, and we can actually just like plug in numbers to get values. I'm just hitting numbers, and it gives me the x value and the y value down there. So it tells me the t value that I entered, and the x value at that t value, and the y value. I can even plug in non-integral values and figure out what happens there. Now, the one thing that the graph does not show you is the direction that the particle moves. Fret not, you can actually see the direction of the particle by starting at the default point, which is at t equals 0, and if you hit right, it advances in the upward direction for t, and you just kind of like trace it, visualize it, see how it's going right and down. Hitting left decreases t, so you're going in the opposite direction of the particle. It's like doing rewind on a VHS tape. Not that any of you know what a VHS tape is. We can go into graph. Nothing changes on that because it's just a graph. If we go into table, that's second graph. You can actually see it has the x value and the y value, and I've got my grapher still set into the ask mode. All right, cool. So that was just a brief tutorial on how to read and how to use your calculator, because right now I'm going to take away the tedium and just say graph these and use the vertical line test to determine whether they are functions or not, whether each one is a function or it is not. So pause this, plug these into your calculator, and then resume. So I'm resuming now. I will tell you that only one of these is a pass of the vertical line test. So it is a traditional XY function, and that is this one. That is the only function on there that passes the vertical line test. And now you guys get to see what I had. Oh, well, let's see. Number 1 is t squared and t cubed. Hey, look! That's my x3 and y3 right there. So I'm just going to turn this on, and I'm going to go over to my graph. Well, I did, logically, since this is the only one that passes the vertical line test, this one fails the vertical line test. But I look at this, and it doesn't look like it fails the vertical line test, does it? Well, that's because my window is faulty. Just guessing here. I'm going to go to negative 2 pi. We're not including any negatives, which do give us some important values, so I'm just going to make it go from negative 2 pi to positive 2 pi. Heck, I could even make it go from negative 10 to 10. Some of you might be saying, why don't I just go from like negative 10,000 to positive 10,000? Because that's going to take a long time. You're counting by 0.13. The further apart you make your Tmin and your Tmax, the longer it's going to take to get from beginning to end. And now you can see it fails the vertical line test. I'm just going to keep this window or this domain on all these graphs. Helps if I turn the next graph on. All right, x4. You can see because that square root, we don't have any values before t equals 0, so that passes the vertical line test. Like I told you. This bad boy, I think, is a sideways parabola. Yeah. And lasty, but not leasty. My favorite one. I call it a fish. It looks like a fish or shark or something. You can mess with the window and like get it a little bit better, like maybe going from negative 4 to 2, negative 3 to 3, something like that. Yeah, I can see the fish a little bit. Oh, I should have gone further to the right. To 4. There you go. Grab that fish. Yeah, cool. Or stingray, something. You can get some really cool graphs. I think in this section in your book, there's actually a butterfly function. If you guys want to look up how to graph a butterfly function. Okay, so next thing that we have to accomplish here is being able to switch from parametric to rectangular. And sometimes it's really easy. Like in some of these functions that we had on that last slide, you can see like x equals t or y equals t. If x equals t, all I gotta do is take that, well, t is x. I take that x value, and in the other equation, I replace t with it, because any t is equal to x. This is the same thing as graphing y is equal to the square root of x. And that's why that graph should look like the graph of y equals the square root of x. Now over here, you can see that y is equal to t. So I'm just going to take the one where the variable equals just t, and I'm going to slide that in for the t value, because anytime you have a t, y is the same thing. So this is going to be the same thing as x equals y squared, which is a parabola that we graphed in the last unit. Now here, this is actually a valuable thing to note here, because this, I'm not allowed to graph it on my calculator unless I go into that Conics app. Now I can actually switch my calculator into parametric mode and graph a sideways parabola, a non-function here, just by saying the independent variable is equal to t, or the traditional independent variable is equal to t, and x is equal to the new independent variable squared. Yeah, cool. All right. Just back you up. There you go. Oh no. Oh no. This one looks bad. So bad. Right? Neither one of them says t equals. So in order to get this in rectangular mode, because again, sometimes we want to switch back and forth, and this just looks really, really freaking complicated. I have to take one of the equations and solve it for t. It does not matter which one you solve for t, but you look for the one that's easier to solve. Traditionally, I've heard some people say that this one looks more difficult to solve because of that square root. This one looks more difficult to me to solve because it's got two t's, and getting the t isolated when there's two of them is a little bit more difficult. This just has t equals. So I'm going to take x equals 1 over the square root of t plus 1, and I'm going to solve it for t. So the first thing is I got to get t out of the denominator. I'm just going to use any algebraic trick that I know how to do that. Easiest way to do that, since I have my numerator as 1, I can just flip this fraction upside down by raising it to the power of -1. So this becomes, this flippity-doodad, the square root of t plus 1 is equal to x upside down, 1 over x. Right? Now I got to get rid of that square root. Get rid of the square root, I square. Again, I'm just using my algebraic techniques that I've known and loved since Algebra 1. So this becomes 1 squared, that's 1 over x squared. This becomes 1 over x squared is equal to square root squared is t plus 1. Oh, why can't I figure out how to get, oh yeah, you just subtract 1. I was trying to make a sarcastic comment that now it's the hard part to get t by itself, but it shouldn't be. This should be 1 over x squared minus 1 is equal to t. Now I've got t equals. When I have t equals, I take that t value and I plug it into the other equation wherever I see t. So this is going to be y equals 1 over x squared minus 1 over 1 over x squared minus 1 plus 1. Perfectly all right for you to leave it like that. The substitution is all we're looking for. I can plug this into my rectangular functionator in my calculator and get it. But that just looks awful. It just does not look good at all. And especially when I look here, I've got minus 1 plus 1. I might say y is equal to 1 over x squared minus 1 over x squared. That just looks slightly better, doesn't it? Now, those of you who have me in class know that I abhor, what are they called? Nested fractions, where I got fractions inside of fractions. Just awful. So those of you who don't have me have not had the pleasure of hearing me say this repeatedly throughout the year. Dividing by a fraction is the same thing as multiplying by its reciprocal. Now I use the distributive property. I now have 1 over x squared times x squared minus 1 times x squared. And let's just clean this up a little bit. 1 over x squared times x squared is 1. Minus 1 times x squared is just x squared. This really awful looking fraction, or parametric function, is the same thing as this guy right here. And that, we happen to know, let's go. Atticus has been saying that a lot recently. Here I was at the beginning of the lesson saying I didn't want to show you guys the annoying part of plugging stuff into my calculator, and here I am doing it. Plus 1 fraction again, t over t plus 1. Because, I mean, just looking at this, I know this is a parabola. If I go to zoom standard, that's a really slow-moving parabola. Let's go from -10 to 10. Let's see if that works. Okay, well, we got half the parabola. At least it looks like what it should look like, right? So that's good. That's good. If you want to look in my notes, I have a different way of solving it in my notes, but you don't really need to know that other way. It's a little bit more complicated. Okay, now for some insanity. This one. I've got x equals 3 cosine theta and y equals 4 sine of theta. Those of you who know me know that variables are arbitrary. If it bothers you, you can call this x equals 3 cosine of t and y equals 4 sine of t, just so that we can keep it in traditional parametric variables here. Now, what I'm going to do for this, I'm going to solve this for cosine of t and sine of t. Why am I going to do that? Well, hopefully I can make that a little bit clearer. I've got x over 3 is equal to cosine of t. Over here, I've got y equals 4. Okay, so I can divide by 4. I got y over 4 is equal to sine of t. Why did I do that? Because I happen to remember from like early January that cosine squared of something plus sine squared of the same thing is always equal to one number. That number is 1. I tried to emphasize the 1 here. What I can do here now is I can have x over 3 squared plus y over 4 squared is equal to 1. And in rectangular mode, I've got x squared over 9 plus y squared over 4 is equal to 1. Which you can go back to one of the sections that we skipped, the section on ellipses. I believe it's 9.2, and you can see that's actually the equation of an ellipse centered at the origin with a major axis running horizontally, and that major axis happens to be 6 units long, and the minor axis ends up being 4 units long. But you don't really need to worry about that because we skipped ellipses. And the only thing left for you guys is the assignment. That video's on our websites. Thanks. We'll see you guys again.